PhD student in the lab. Sam graduated physics 2023. He's been in the lab for 2 years, developing these bespoke imaging processing tools. And given the spirit of this seminar series, Sam is going to share his approach today in wood and paper. Sam is also developing an open source. He's sort of giving away these codes. You have an open source tool for a number of them. Well, if interested, you can check out Sam's tools. Okay, Sam, if you would.
All right, thank you, Mark. Yeah, good wire there. Okay, yeah, so thanks for coming, everybody. Scan the QR codes and whatnot. I'll show that again at the end. As Mark said, I'll be talking about some case studies that we've done in wood and paper samples over at the Pulp and Paper Center. Hopefully striking a good balance between methodology approaches and then just a brief discussion of some of the results also. But while I have a captive audience here, I'd take the opportunity to do some advertising as well about the X-ray microtomography instrument that we have next door, which some of you may have used. So I'll go into some detail about that and how the protocol works if you would like to get a scan with us and sort of the principles behind it. And then look at an application of this tool to a study that we did a little while ago, looking at uniaxial compression of wood. So that's along the grain looking like that. And in that instance, we were interested in assessing the microscale defect evolution. So how the fibers are deforming over increasing levels of strain. And the tool we used for that, we developed a neat image processing pipeline to track these wood volumes over time with 3D deformation profiles. And then the second study, another application to fibrous porous media, is looking at wicking in paper. So that's the phenomenon that when you touch a piece of paper to liquid, it spreads out beyond the original contact point. And what we want to understand there is the pathways that the liquid take at the microscale, because despite it being such a ubiquitous everyday thing, it's still not too well understood. And there we have a few different tools that we use, like fluorescence microscopy, X-ray radiography, and optical coherence tomography. But first, I'll start with that overview of the X-ray microscopy instrument that we have. So just in a schematic view, this is the general principles behind X-ray microscopy. You have your X-ray source, which finds X-ray on your sample, gets detected by a detector. In terms of a chronology, we have the X-ray radiation, which penetrates the object. The object casts this sort of shadow on the detector. And then this stage is capable of rotating in very fine increments, rotates and catches another projection. Does this a few thousand times, and then at the end, everything's reconstructed into your 3D volume, which typically comes out as a stack of 2D image slices. And of course, you're capable of looking at it as 3D rendering too. You should become familiar with this Playmobil figure. He's our lab mascot, and we find it as a useful demonstration tool to explain these types of things. Also, whenever maintenance is done on our machine, a bit of a reality check that things didn't get messed up and all of a sudden his feet are in his head or something like that. In terms of our specific instrument, though, it's this Zeiss X-Radia 520 Versa. On the outside, it's in a big metal box to shield against radiation. And if you look inside, we have those same components: the X-ray source, detector with a variety of objectives, sample which sits on a motorized stage. In terms of pricing, there's a $100 per hour flat rate, which is used for our technician James to set up the samples, and then also $70 per hour source time, because the source does degrade, and that's just to help us replace it down the line. We're not making a profit. And then, unlike some other instruments on campus, all scans are acquired by James, not a use it yourself thing. But nonetheless, I thought it might be helpful to go through more or less a day in the life of an X-ray microscope technician and how one would acquire a scan. It might be informative for the characterization audience. So one of the first and arguably most important steps is the sample preparation. Although it's typically thought of as a non-destructive technique, it can actually be pretty helpful to destroy your sample a little bit first and get it down to as small as possible. And you also need to be mindful about things like stability, thermal stability, evaporation, things like that. If it's changing at all over the process of the scan, it's going to lead to poor results. And the motivating example there, this doesn't show up too well on the projector, but we had a chocolate manufacturer reach out to us. They were having some strange problems in their chocolate, and just as a proof of concept, we put a aero bar in there to see if it could stay in the inside of the warm machine without melting. And in fact, it did. And fortunately, it doesn't show up too well, but it got a cool looking image of an aero bar. Once your sample is mounted, you have to align the stage coarsely on your area of interest. So this is when it can be helpful to have some rough sense of where the feature you're interested at looking at in your image, in your sample lies. Once that's done, the magnification comes in. It's an X-ray microscope, so this is a very important step. And really, the first thing to think about there is the objective to use, and that sort of locks in the pixel size range that you'll be having. So at the biggest, at the highest end, we have a 60 micron pixel size, all the way down to 0.2 with the 40x objective. So that's sort of the coarse selection of your pixel size, and then we set the source detector geometry to fine tune the pixel size. So this affects the geometrical magnification that comes in. Basically, you have this triangle of X-rays coming out from the beam, which casts this shadow on the scintillator, which then goes through the second stage of the optical magnification. And the geometry of this triangle is going to be what dials in the pixel size closely. The specific relation is that the source detector distance over the source object distance, and there's a big boring trigonometry proof you can go through if you're interested in more about that. But essentially, then your pixel size will be dictated by the inherent pixel size of the detector divided by this geometric magnification factor and the objective magnification factor. But in reality, what we most often do is just position the sample as close to the source as possible, and then just tweak the object detector distance, because by moving the sample closest, you expose it to the greatest amount of flux, which typically leads to a nicer image in the end. Then, so once that's done, you have some more optimization to do, namely the voltage of the X-ray source, which sets the photon energy. So at the highest end with this bigger, the X-rays pretty much just blast on through and it turns more and more transparent. At the lowest end, you can get some better contrast between the different types of plastics in there. So this is a very sample dependent choice. Typically for our cellulose materials, we're in this 60 to 90 range, whereas the materials folks like to bring huge chunks of metal, and then you really need to crank up the voltage in order to get the X-rays through there. And then there's also the power, which determines essentially the number of photons that you're sending at the sample. Higher power leads to a better signal to noise ratio typically. So this far, it's been about optimizing the 2D image. When you go from 2D to 3D, really the main thing you're going to want to modify is the number of projections. So at a higher number of projections, this was actually pretty low, but it was a simple sample, so it was sufficient, typically 3,000, 4,000 range. Your reconstruction algorithm has more data to work with compared to a lower number. You can see it's a choppier angle increment. So you could imagine how it might lead to a worse quality image in the end. And then there's also things like exposure, essentially a shutter speed for the camera, which can, again, reach the signal to noise. We have some additional capabilities on the instrument. We can do in situ testing, a bit of what I'll talk about today. We have a compression and tensile stage, and allegedly temperature control, even though we're not too sure where it is actually. And then there's a dual energy scan mode, which I don't think we've ever tried, but it helps you to do essentially lab scale crystallography and distinguish between different materials that are very close in density or atomic composition, better than we'll be able to otherwise. And then there's also a phase contrasting mode, which I think we also haven't really used. And that helps delineate between the different phases and phase boundaries in the material. Now, just to highlight a few of the different things we've looked at. One of the first comprehensive studies we did was looking at the contacts between assemblies of spheres in there. So by changing the sphere diameters and stuff, how does that change the ways in which they're contacting each other? We did a study recently too on carbon nano fiber films for food packaging applications that had mercury intrusion porosimetry done on them. So this was to reveal the pore space inside there. Just in the past few months, we've had some people from zoology bringing us these cicada heads, and those turn out very nicely on the scans. Too nice that I don't even really like looking at them too much. And then at the greatest level of magnification, we've had some people from materials engineering bring us some little pieces of metal where we get down to the 200 nanometer pixel size range, get some very intricate details on those. And then what I'll be talking about today is our paper samples like that, and also our wood samples. So that leads me in now to the case studies which we'll discuss. So I think it's recognizing the various backgrounds here. Start by looking at the microstructure of wood. The main thing to be aware of is that there's two forms of these longitudinal voids in there. The bigger ones are called vessel elements, which are primarily responsible for liquid transport in the tree. And then if there are any people who are familiar with wood anatomy, they may take offense to this, but we just classify the smaller ones altogether as just generic fibers, although more types do exist in reality. And these are the ones that provide mechanical support and are used in paper making. So we're interested in assessing the fiber defects as we progress through increasing strain. And then they're all interconnected by pits as well to facilitate the liquid transport. And this makes segmentation difficult, as I'll further discuss. So the context behind this project, pulp and paper industry is big in BC, of course. Trees are the primary ingredient. The good parts get taken for lumber. The not so good parts get turned into wood chips, get sent off to the pulp mill, and then turned into whatever paper product there is. One stage in this pulping process, specifically mechanical pulping, involves the compression of these wood chips along the grain. And in here, various defects come about, and we want to investigate those in a little bit more detail. It's known that these defects manifest in two primary ways: buckling, which results in the translation of fiber ends against each other. And then there's also this one, telescopic shortening, which is more an accordion-like crinkling of the fiber. And here, these micro compressions come into the wall. This is an image taken from later in the study where we've isolated some of these fibers digitally from the wood matrix. We can see that the micro compressions coincide with buckling, but when the ends remain aligned like this, it's called telescopic shortening. We know from single fiber tests and things like that, that buckling can reduce the tensile strength of paper, which is a bad thing. Meanwhile, these micro compressions can increase the extensibility of papers and stretch a bit more, which is a good thing. So from an industrial point of view, we might be interested in how can this telescopic shortening be induced systematically, and how do these micro compressions develop? And for that matter, how does buckling develop at the microscale? And these aren't too well understood, so that's what we wanted to investigate by tracking the fiber evolution with our microscopy. So I already showed this before, but now we have our in situ compression device on there, which we just built out of a micrometer head that we could twist down and put whatever level of compression we wanted. And we carried this wood sample out over 10 different compression steps with a scan at each step after a short relaxation time. We turned the micrometer by 30 micrometer increments to increase the strain. Scanned at a 1.2 micrometer pixel size. Sorry, that might be hard to see, and that is a 2 millimeter field of view. So just to begin with the overall qualitative view of what we're seeing there, this is now the side cross section of the wood, so we can see what's going on with this the buckling fibers. Initially, everything's very nice and straight. And then if we skip ahead to the fifth step, we see not really any huge difference, just it's a little bit shorter than it originally was. But then by the end, especially near the top here, we do start to see some buckling come in. But in order to analyze this further, we need to develop some quantification tools to see what's going on. So that's where image processing comes in. When you get the raw image out of the micro CT, there's often quite a bit of noise in there. So one of the first steps always is to filter the image. That helps to increase the contrast in this instance between the air air and solid wood cell wall. Then the next step after that generally is to binarize the image, so that is separates it into two classes, foreground, background. Here we want to see what's happening, mostly tracking the fiber lumens over different steps. So we split it between those two classes with a simple integer threshold on the histogram, which separates the pair cell wall. Then we move from that to a labeled image. So that's where each one of these void spaces now has a unique integer applied to it. And then that's carried out in 3D. So you end up with this whole 3D labeled image. But this is a fairly complex step most of the time. So I think it's worth spending a little bit more time on how we did that. The basic approach for these types of problems is basically a flood fill, like the paint bucket in Microsoft Paint. You just click on one area and it labels all the connected components. But we have these pits that I mentioned earlier, which can lead to basically under-segmented image where things are joined together in a way that we wouldn't really want. And in fact, when we found that if you just do this simple labeling over the whole wood volume, you just end up with one label everywhere, which isn't very useful. So instead, we use a different method that consists of a distance map and a watershed transform. So the first step here is to do the Euclidean distance map, which essentially counts from each black pixel what's the distance to the nearest white pixel. So it looks like that in the end, or you can think of it instead as this elevation map where the parts that are furthest from the white pixels are deep valleys in the image. Then this watershed transform comes in, and this is really quite I think this is how more or less it was developed. It draws from the geographical feature of these hills separating the valleys where water fills. So now you go to each local minima of the image and start to fill those, and then wherever these different pieces of water start to touch, you draw a line. And when we do it this way, we can essentially close these pits and end up with better segmentation. So with this whole segmented volume, then we can just select whatever integer label we want and extract those individual fibers. And then in a semi-automated way that I won't get into too much, we can track those through time over the different compression steps. So for example, this fiber here, we see from the first step to the 8th compression step, it's shortened slightly to translate downwards. And then through to the end, we never see any buckling come in. But because we do have this shortening, it's likely that telescopic shortening deformation mechanism. On the other hand, this one here, we see that it again translates downwards and compresses slightly, but then by the end, it's developed this kink at the top. So this is the telescopic shortening before buckling mechanism. And so we can take this methodology and apply it over the whole wood volume to look at the spread of deformation and come up with a systematic way to determine whether or not a fiber has buckled. We do that by taking some fiber on the nth compression step. We can trace out the centroid path, and from that to get the inclination angle of the fiber, and then subtract that from the first step, which we use as a reference to look at the change in the inclination angle over the fiber height. And in cases of buckling, you tend to have a big spike in there somewhere. So then we can apply this classification over a wider field of view. And in this case, we see no buckling from step 1 to 6. And on steps 7 and 8, this red colored region here indicates that those fibers have begun to buckle. And then it spreads on the 9th step. And then the 10th step, this whole field of view is deformed. We notice, though, that this tends to be quite heterogeneous. So, for example, here on one side of the volume, we have fairly straight fibers, and then on the other side, we have buckling. So we are also interested in seeing, can we make some anatomical correlations to the wood that maybe there's weak spots around there somewhere. And to do that, we can look at it a little bit more chronologically like this, where these red colored regions started to buckle on the 8th step, and then it spreads to these green regions, it spreads to the blue regions. And by looking at that, we were able to deduce some information about the wood anatomy that might be adding weak spots or strong spots metrics. And then we also use this methodology to identify a critical strain limit for this type of aspen wood that potentially could be used to induce these beneficial telescopic shortenings of fibers. So this was just one example of how we can use micro-CT to study dynamic processes and porous materials. We were able to identify this critical stream on it. Notice that this telescopic shortening before buckling is a pretty common pattern. And if you want more information, I won't get into the results too much beyond that, but we look up our publication. I'll now move on to our edge wicking study. And as I did with the wood, I'll start with the microstructure of paper, because I know at least when I did my first internship at the Pulp and Paper Center, I never had thought that closely about paper. I knew it was composed of fibers, but didn't know beyond that how much more complex it really gets. Here's a SEM image of a cross section of a piece of paper, and then this is a micro-CT image looking at the top. This particular sample had been ripped in cell testing, and you can see all the different fibers which are joined together. And what we're interested in about with its interactions with water or liquids is the pore structure, and there's a bunch of different types of pores across different scales here to consider. From biggest to smallest, we have the interfiber pores, the spaces between the fibers, which are typically around 30 microns in radius. And if we zoom in more on a lumen, or on one of these individual fibers, we have the fiber lumen, which is the same as the wood lumens from the previous project. These are around 10 microns in radius typically. And then there's also these tiny little surface channels based on rough models of the fiber that are more at that scale. And we look at a different one here. This particular one has been delaminated, so it's a bit easier to see. We see that the cell wall itself, whereas it looks solid here, in reality it is porous. And then there's also these intra-fiber pores in the cell wall, which are also in the nanometer scale. So all of these present potential pathways for the liquid travel. The specific type of liquid transport we're interested in here is called edge wicking, and that's where we have basically immediate saturation in this direction and in the depth direction of the paper, and then the flow is primarily going upwards like this. And it turns out in this type of situation, despite paper being such a material that interacts with water every day, nobody can quite agree on where the liquid is actually traveling at the microscale and how it's traveling there. As I mentioned before, there's all these different pore systems, so it could be going predominantly at the outside of the fiber, primarily through the fiber lumen, or filling up these interfiber pores, or traveling through the intrafiber pores in the wall. And again, it's a controversial topic, and nobody can really agree on why or how it does that. And of course, it's important to understand this for many developing fields like these micro paper-based analytical devices, and then also hydrophobic treatments for paper products and stuff. So you don't have the very standard Vancouver experience of your paper bag exploding your groceries all over the parking lot on a rainy day. And so this process of edge wicking is well described at the macro scale. It's been studied for about 100 years using typical capillary flow models. And when we look at it in this framework, zoomed out, we see that the force that's propelling the liquid upwards, the suction force, is proportional to 1 over the pore radius. Meanwhile, the downwards force is proportional to 1 over the square of the pore radius. So when you balance these forces out, we find this so-called Bell-Cameron-Lucas-Washburn, or BCLW equation, which says that this rise height as a function of time is proportional to the square root of the radius of time. So this fits experimental data quite well, typically. And based on this equation, we have this square root R term. So our assumption would be that the water in the bigger pores should travel fastest. So this in this view of paper, it's going to fill these interfiber spaces first, and then probably the lumens. And then we know that the fibers themselves are wet eventually, but the pores in the wall are so small that it seems radial diffusion is the most likely pathway through which that happens. So in a cartoon view here, with our just vertical fibers, we have the spaces between them filling first, and somewhere behind that should be the lumen flow, and then radial diffusion into the fibers. So that's our sort of naive assumption based on this framework. But then it turns out that experiments don't necessarily agree. There's a study done about 10 years ago, nice fluorescence microscopy videos, which showed that it's not actually the spaces between the fibers that are filling up the fastest. Rather, there's this precursor front, which goes ahead in those microchannels on the outside of the fibers. And no evidence of lumen transport either. But these microchannels are so small and they have a way higher resistance. So this there must be some additional mechanism going on beyond just the capillary pressure that's driving the liquid. Turns out that this is well supported by a theory of interphase mass transfer that says when you have two tubes that are connected together, the smaller tube can essentially steal liquid from the big one because there's a higher suction there. So it can steal this liquid, which helps to overcome the extra resistance that it has also. So we have this precursor front, which is going along. And we did a study a few years ago using iron tracers on a piece of paper. So we bake in this soluble iron compound into the sheet, and then dip it in a basic liquid, which causes the precipitation of these iron nanoparticles. Then we wash off the unreactive iron. So we have these nanoparticles that are left behind in all the areas that we're experiencing that were wet during absorption. And wherever there's more iron, there would have been more liquid at the point in time that we stopped the reaction. Then when we look at this, we can first examine the fully immersed region that was down in the Petri dish. And we see that from EDX and micro-CT, we have a profile of more iron on the outside of the wall than on the inside of the wall. So this is showing radial diffusion to us. If you think back to heat equation, this is like the high temperature on the outside of the wall, low temperature on the inside, you get a linear look gradient like that. Meanwhile, up in the wetting front, where the capillary suction is occurring, we have more of a flat profile, which is actually consistent with axial penetration. So we don't have that radial diffusion into the fiber wall up in this wetting front area like we would have expected based on the basic capillary principles. We have axial flow in the fiber walls. But again, based on the pore sizes, this really shouldn't be happening. In fact, it should be about 100 times further back than the flow in the other domains. So we wonder if there's another mechanism that's causing this speed boost like there is with the precursor front on the outside of the wall. And we do some experiments to determine what's going on here. So before we zoom in too much though, this our iron tracer method was in fact a static measurement. So we wanted to get a better idea of the dynamics, which we did at the macroscopic scale. And there's some saying of when you're the only tool you have is a hammer, everything looks like a nail. So we use our X-ray camera to take pictures of everything. And we use that to get these time-lapse videos in 2D of the water moving up through the sheet. So that's what that looks like with the liquid being yellow here coming up. We can average across that and look at it this way instead as a spatiotemporal plot. And now you see the dry paper separated from this saturated region, from this sort of diffuse bluish green saturated wetting front moving through there. So just knowing what we know about the volumes of the different pore sizes in the paper, it's likely that all this yellow stuff is those big interfiber pores filling, and we can't get too good of a sense of what's going on inside the fiber wall specifically here, although it does give us a good overall picture of the saturation. But to figure out what's going on inside the fiber walls, we need to use a different type of measurement to give us an analogous quantity. So here we turn to optical coherence tomography, and that gives us a measurement of height. It's a profilometry method, more or less. So we can watch the swelling of the paper as it goes along. And when it comes to cellulose fibers, swelling basically only occurs due to liquid interactions in the fiber wall. So this is a reliable analog of the degree of the filling of those small intrafiber pores in the fiber wall. And we can do a similar type of analysis here. But then to deal with the very different fields of view of these two instruments, we kind of need to put everything onto an even playing field and do some domain transformations that I won't get too much into. But essentially, we were able to confirm at the macroscopic scale that this axial fiber flow is traveling at a much higher rate than we would expect due to capillary suction alone, which is what we're seeing here, that right on the wetting front, they're closely aligned. That it's only following slightly behind the rest of the saturation. with that confirmed, we want to now address why might this be happening. We think it's this stealing of liquid from the bigger pores, and in order to so looking like that in our cartoon representation, then in theory, if we were to make sure that this mechanism couldn't happen, then the liquid should slow down if we remove this speed boost. And it turns out we can do that with a sample of some commercial hydrophobic paper. When they make hydrophobic paper commercially, they basically put a hydrophobic molecule everywhere on the outside, so between the fibers, on the outside of the fibers, but the emulsion that it's in is too big to go inside the fiber walls. So those remain still a possible way for the liquid to flow. And then if we look at this with fluorescence microscopy, we're basically guaranteed that whatever signal we see in here is purely just due to the capillary suction wall. So we can take some fluorescence microscope videos of this happening, and we see a clean image of just water traveling inside, or fluorescent dye traveling inside the fiber wall. Meanwhile, though, if we look at just a sheet of normal paper undergoing this same experiment, it's quite a bit more varied. We see liquid filling the spaces between the fibers and zipping around all over. So we, if we want to just see what's going on in the intrafiber pores here, it's difficult to do. We can't do it just visually. So we needed to come up with a way to measure the flow in the intrafiber pores to see if it's going faster in a normal sheet with this mechanism occurring than in a hydrophobic sheet where this couldn't possibly happen. For that, we developed this dual staining protocol for our confocal microscope. So we first capture a static background image of the paper that has been pre-stained with dye in one certain color. And then we basically do a pixel by pixel classification on this image to identify for each pixel, does it belong to a fiber, does it belong to a space in between the fibers? And then we flow this green colored dye, as I said before in the videos on the last slide, to capture the dynamics of the imbibition. And then with this image segmentation, now we can take this dynamically flowing dye and determine which domain it resides in. So we can make some videos now looking like this, where we've colored part of just digitally dye that we've identified as being in the fibers in red, and that the interfiber pore dye is in blue. And this now allows us to analyze the dynamics of these two domains separately. So as before, we can now look at some spatial temporal absorption here. And we see in the fibers, we have a pretty clear delineation between two fronts coming in here, one moving up there and then one slightly behind like that. Meanwhile, in the interfiber pores, it's really more of just a gradual uniform filling without such a clear delineation between fronts here. So we did some more analysis and compared it to the macroscopic results, and we feel pretty confident that this second front here represents the filling of these intrafiber pores. So if we just ignore the first wave and look at the second wave, then we can quantify the rate that's these tiny pores in the fiber wall are filling up. So now we're equipped with this measurement tool. We can compare the normal and the hydrophobic paper to see if blocking these external domains slows down flow inside the fibers. Here's just an example of a digitally isolated fiber from one of these hydrophobic paper sheets. And we can look at the saturation of the intrafiber pores over time like this. And then with just a control sample of some normal filter paper, in the usual way, it'll move across first and then start to gradually brighten over time. Sometimes we don't really know why. It'll move along first in one direction, and then the intrafiber pore filling will happen in the other direction. Here's a frame by frame difference in that video just to accentuate that. In either case, however, if we take only this second front coming in, we can look at the saturation over time there as well. And it turns out for the control sheet, it does happen much faster. So this is suggesting that when you have these external domains open, the fibers might be stealing liquid from them, which is speeding up the flow. So it's a bit of a tough argument to follow, but essentially, summary of that is that we've found with our previous measurements that the liquid inside the fiber walls is traveling much faster than we would expect, suggesting some sort of speed boost happening. And we confirmed that it is indeed traveling quite quickly there using X-ray radiography and optical coherence tomography. And then we devised this dual staining approach to distinguish between the dye in the different domains of the paper, inside the fibers or outside the fibers. And we have some pretty promising results that shows that blocking these interfiber pores slows down the intra-fiber pores absorption. So there must be some sort of link between the two. That's all I have for today. Thank you for listening.
Oh.